Hi, this is Dr. Rosario, and this is our first lecture out of Chapter 8. Chapter 8 begins our unit on metabolism. So metabolism is all of the different chemical reactions that support life. And in order for us to understand those chemical reactions, we first need to understand what is energy. So that's going to be the topic of our first lecture today. So I'm going to define energy for you. I'm going to talk about the relationship between energy and work. I'm going to discuss the different types of energy and then the laws that govern energy. So the first and second laws of thermodynamics. And then finally, I'm going to differentiate between exergonic and anergonic reactions. Okay, so your book has a definition of energy. It says it is the capacity to do work. Now, when we say work, that can mean a variety of different things within a cell. That can mean building biological molecules. It can mean a pump transporting molecules across the plasma membrane. It can be a motor protein walking along the cytoskeleton of the cell. So work can mean a lot of different things within the cell. So energy is the ability or the capacity to do that work. A better definition for energy, one that I like, is when something is moving, that is an example of kinetic energy, right? The process of movement. And then the potential to move, right? If something has the potential to move, we call that potential energy. So here are some examples for you. Here I have a river and it's flowing downhill over a waterfall, right? Those water molecules in that river are in motion, so they have kinetic energy. Here I have another river where the water has been stopped by a dam. In this case, this is an example of potential energy because that water is stored up behind the dam, and we actually use dams as a way to generate electricity, right? Water flows through that dam and it turns turbines, and that will then produce electricity that we use to power our homes. Here's another example of potential energy. This is a candy bar. And in a candy bar, you have chemical energy. Chemical energy is the energy stored in our molecules. So your candy bar has lots of energy in it, right? When you look at a nutritional information on the back of your candy bar, you see the number of calories. It's actually kilocalories, or the amount of energy stored in that candy bar. Now we can see that candy bar energy put into action when I feed it to my children, right? So here's my kid and he is jumping off of the side of a little hill of sand. And in that case, he has taken that chemical energy in his food and he's converting it to action, right? So this would be another example of kinetic energy. Sunlight is an example of kinetic energy. You have photons of light that are moving from the sun across space. Now, living things capture that energy in the process of photosynthesis, and they store that energy in the bonds of organic molecules. So in living things, we have a lot of potential energy in our biological molecules. So this brings us to the first law of thermodynamics, which is that energy cannot be created or destroyed, but it can be transferred and transformed. Okay, so energy can change form, but it is not created, it is not destroyed. All of the energy in the universe is constant. It is changing forms, but it is a constant amount of energy. The second law of thermodynamics states that while the energy can be transferred and transformed, there is a constant increase in the entropy of the universe, an increase in disorder. So entropy is disorder or randomness. So every process that we have that transfers energy from one form to another is going to increase the overall entropy of the universe. And we can see entropy in action, right? So this is my kid's bedroom. I swear it was clean 5 minutes before I took this picture, but here you can see it is constantly going to be moving towards disorder, right? Disorder is a universal constant. So a spontaneous process is a process that leads to disorder. It increases the entropy of the universe. So here's an example. I have a large biological molecule. It's being broken down into smaller components. That is a spontaneous process, and as a result, energy is going to be released. We say that that process is exergonic, all right? It's directly increasing the entropy of the universe. It's energetically favorable, and energy is exiting the system. The opposite of a spontaneous process is an endergonic process. So here I have small molecules that I'm going to put together to build a larger molecule. That requires an input of energy, right? This is not energetically favorable. It's not spontaneous. We're going from disorder to order. So in order for that to happen, we have to use some energy. So this process would be endergonic. Now, I said that, entropy is constantly increasing, right? So when you think about that in the context of life, life is energetically unfavorable. Keep in mind, what is it that is driving life? What sustains life on this planet? It is the sun. It's the energy of the sun. So now we have to think about the big picture. The sun is this ball of gigantic incandescent gas releasing tons and tons of heat and disorder into the universe. A very small amount of the energy from the sun is used to sustain life. But then as life is sustained on this planet, the energy of life gets radiated back out into space in the form of heat. So while life is an island of low entropy, entropy across the universe is constantly increasing. And in order for life to be sustained on this one planet in the universe, we have to have a constant input of energy from the sun. Okay, so that's your introduction to energy. We're going to talk about energy some more and endergonic and exergonic reactions a little bit more as we go through these next couple of lectures. So this was really just an introduction to the ideas, and then we will get into the details in the next 2 lectures.